Right. Well, look, it's 5:30, 7:30. Yes, a few of us are here. Everybody, hi. My name's Stephen. You're all very welcome to put your microphones on. I'm quite happy to take questions as we tickle along. What I will ask is that if you do find yourself that your phone's ringing or you need a loud conversation, just don't forget to mute your microphone. But apart from that, I see your microphones are all off. You're all welcome just to switch them all on. I'm assuming that's all within your power, not mine. I think I can turn you off. So, tell you what, look, at 7:30. There goes Ward. Hi, Ward. He's connecting his audio. Right, okay, so I'm not sure if we've got new people joining us. There's a few first timers who were going to join us. So this is Makespaces in Cambridge, how to design electronics. This is season 2. And this is episode 5, and this session is going to be on, as per see hopefully on your screen, the title. These sessions are really just about giving you some simple ideas for designing your own electronics. It's all based on my experience, having done a lot of this for nearly 30 years. It is live, of course, so anything can go wrong. The most common thing that has gone wrong in the past is we've lost the picture quality. So it looks great at my end. So if it goes flaky at your end, then someone needs to pipe up, and then we'll try and fix it all together. What I've got for us today, everything can be downloaded, so you don't need to worry about taking copious notes. So on my website, hopefully you can see that there. The downloads for these slides on AI, and I've got some stuff which I've done in Excel, which will swap to a different screen. All of that is loaded up already on my website, Silicon Cortex. So if you tick along to that website, scroll down to downloads, and it'll take you to something called Box, which is just a storage site. And you'll see how to design electronics as one of the folders. Click in there, and then you'll be able to see season 2, you'll see season 1 there, and within that you'll see episode 5. It'll say HTDE AI, and there'll be these slides and there'll be an Excel file. So you're very welcome to grab those at any time. So sit back, enjoy, and any questions as we go along, by all means just interrupt me. Otherwise I'll just wax on for 20 minutes and then we can sort of rip everything to bits and have a chat. Right, okay, so let's start with, for those who are new to this, I've got a picture here of what is AI. So this is just a very simple breakdown here, just to set the scene. Within the title of artificial intelligence, it can be broken down into a number of subsections. One of them on the left here, as you can see, is called machine learning. And this is the one which we're going to be having a play with this evening. And so really, as we'll see, that's mostly just about algebra and statistics. And we're not going to do calculus this evening, but it's that kind of thing. It's schoolyard mathematics. That's all it is. Machine intelligence is a build upon machine learning, but you're adding anything to get the job done. So it could just be, I need to throw a switch in to make my AI work, where it's not necessarily really AI, it's just anything extra to get the job done. That's all it is. And this is the area which I'm particularly interested in with a lot of the work which I'm involved in. Then you skip on something which you've probably heard called deep learning. You hear about Watson playing chess with people. This is all your neural net stuff. This is all the really clever stuff, all the maths where all the big money goes. And then moving along a little bit further, there's something called artificial intelligence, title within title. So that's not very well thought out.
I think I've lost signal. I don't know if anyone else has.
Me too.
Hopefully I've still got you there. It said recording in progress.
Yeah, back.
We lost you completely for a little bit.
Brilliant. Hang on a second. I think that might, one second, everybody. I think share. Let me just put that back on. Is that back? Where did you lose me?
You were just saying artificial intelligence.
Oh, okay, right. So let me just rewind for 2 seconds. Sometimes it does suddenly said on my screen, recording in motion. So Ward, you'll have to stitch that together later, probably. Yeah, so just sort of mentioning artificial intelligence is, it's a build upon deep learning plus anything else to get the job done. So everything is really building upon everything else. In my view, they probably should have called it something else, because having artificial intelligence under the umbrella of artificial intelligence is all.
Gone again, I'm afraid.
Right, so, or machine intelligence, anything to get the job done. I'm sorry?
Yeah, you're breaking up.
Oh, hang on a second. We're having this game, are we? Right, one moment. Last time we did this, I changed the resolution. Let's just see if that's right. We changed resolution last time this happened. Right, I've dropped the resolution on the present screen. So is that sounding okay for the moment?
Currently.
Okay, right, stop me when it all goes wrong. It sounds like we're in for a ride tonight, doesn't it? Right, so machine intelligence. So as I say, it is anything to get the job done. It's just good old algebra, which we're going to have a tiny tinker with. Yep. Hang on a second, my time is all gone a bit funny. There we go. Right, it's good old algebra, just what you did GCSE maths, nothing more. It's statistics, which goes back to the 17th century, so there's nothing new there at all. And then you hear this fancy word called regression, which we're going to have a look at in a moment. And it sounds scary and big and brave and new, but I'm just about to burst that bubble by giving you a bit of a tour of that's easy. We're not going to look at calculus this evening, but for anyone who's done A-level maths onward, will know things about areas under graphs and doing gradients of curvy lines. And it's only actually when I started tinkering with this stuff that after 30 years, I actually found a use for double differentiation. So that stuff I did back at Long Road in Cambridge back in 89, 90, 91. I did my A-levels. Didn't really mean a lot then. Now it's suddenly extremely useful. And the other thing which I've been bringing to the party as my stuff with machine intelligence is this bottom one here, which is about giving your application some background information on what it's doing. So as an example, if you were to employ somebody to do a job of work, you would employ them because you think they know something about their subject. And that's exactly what I'm saying here about machine intelligence. It's about giving yourself a foot up on the ladder of anything added for the application that'll just make your life easier and run smoother. So for me as an electronics engineer, obviously I lean on 30 years of, got many t-shirts on many different subjects. So that's all you need to worry about. So I thought what we'll do is we'll have a little look at the linear regression to start with. And then I'll show you a few other tools. And all these things, you can do all this in an Arduino Uno. It's that easy. Right. So, this is when hopefully nobody will glaze over. Right. Okay, this is also on a download. So if your screen goes wonky, you can always get this on the download. So linear regression is very simple. If you imagine you had an XY graph, X and Y, and you had a straight line. If you remember your GCSE or O-level maths, you remember it was represented by an equation of y equals mx plus c, where m is the gradient of a line by how much along and how much up, and then c is where it cuts the y-axis. So in machine learning, this is called supervised learning. I've given it a name, nothing special. And what we can do, this is, you'll find this in a statistics book. I got it out of this one here. Hang on. This is, I'm not kidding, this is teach yourself statistics. Got this on Heifers in Cambridge for a few pounds. They priced about 15 quid. That's all it is. And it's got all of this in there. So you don't need to go and buy a special book or do a special course. So what I would say is when you're looking at all this, don't worry about where the maths comes from. Trust it.
Looks like the picture's frozen again.
Let's,
Completely gone now.
oh, hang on. We lost again, didn't we? Hang on, everybody. Let's try. Visualize. Right, are we
I
back?
was wondering, Stephen, if you switch your camera off.
Yeah, that's
while-
not a, yeah, that's a really good idea. Right, one moment, hang on a second. Let's try, and one moment, everybody. Yeah. No. Stop, no, not stop video. Stop video, would that do it?
Yeah.
Yeah, right. Okay, so right, where did we get up to?
Well,
we-
the bit that I got clearly, you included y equals mx plus c, and then you were starting to look at
Okay,
m
right.
equals, and then it all went to pot.
Okay, yeah, I'm sorry, everybody. There's nothing I can do about the video quality. Right, so what I wanted to describe for us here is, so imagine we have a XY graph and we've got a straight line through it. And these green crosses are, say, our data points. And we're going to draw a line through it all. So in linear regression, there's a very neat way to actually work out what the gradient is from these data points. And I've got another example in just a moment we'll have a look at in Excel. So what I would say, hopefully it came across, is when you're doing some of this stuff here, don't worry too much about, trying to understand the maths behind it. There's no need. Just break it down into bite-sized chunks and just use it, and it will work. So this gradient, I'll just explain here what this all means here. So m is the gradient for this equation here. N here is the number of sample points. So here we've just got n equals 4 because we've got 1, 2, 3, 4 points. And then this funny notation here, this first one here, what this is saying is you take the x value there, multiply by the y value, and you'll get a number. And then repeat that number. So let's call that, we'll call this number 1. So we'll call this x1, y1. We'll call that x2, y2, x3, y3, x4, y4. Yep, hopefully that's, you can see that okay. And then this funny thing here just means the sum of. So just add them together. And then you can see, you can probably get the idea of, well, this one here is just going to be adding x1 plus x2 plus x3 plus x4. That'll be a number. And then this will be a number of y1 plus y2 plus y3 plus y4. And then just those two numbers, just multiply them together, store them as a number, a variable. Similar thing for the bottom. And then just use a simple bit of code just to add them all up. So you could do that on one line, line 1. You could put that on line 2, that on line 3 in a code, that on line 4, and then line 5, you'd just be able to just do a very, very simple piece of algebra. So like I say, just break it down into bite-sized chunks. Don't worry too much where this all gets derived from. And then for the C here, very simple, is you just have to rearrange this equation. It's a simple piece of algebra. Well, C equals y minus mx. And the mean here just means taking the average. So the average of all the y values and the average of all the x values. And that'll tell you what C is. And I guarantee that will work every time. So whereas Ruth was saying, you know, about in the beginning of our conversation, of you can get an idea as to what's going on in a system, electronic system, could be temperature, and then you can, from the data points, you can
Lost the sound again. And the picture.
Not doing well today.
right, we're back. How many times is this going to happen this evening? Right, okay. I'm hoping I managed to convey that to people. A little bit of maths. No. What's this? What's this? Hello?
Yeah, we got you again.
Yeah, we're here.
You're there, are you? I think it went again, didn't it? Right, what I'm going to do is I'm going to change this screen now because I was going to show you it actually working, this piece of maths that we can use. So I'm just going to unshare a screen and try and reshare a different one. And hopefully I've still got everybody. Because what I've done here for you all. Right, okay, so can you see the Excel spreadsheet on your screen? Yeah,
Yeah, it's all there.
Brilliant. Okay, I hope I haven't lost people here. So here's an example of it actually working. In this example here, on the x-axis, I've made it just minutes, and and on the y-axis, I've just done an example of temperature readings. And so every so often, I've taken a temperature reading, and I have then plumbed that into these very simple equations, which you can download, and it'll tell me exactly what the gradient is, and it'll tell me what the offset is. So it'll tell me what the straight line is through that. And if I go to another one here, where things are a little bit further apart, it still gives me a pretty good estimate for what that graph will be. And it's just a few lines of code, so I guarantee it'll work every time for you. It'll also work if you're doing something going the other way, negative. So hopefully you can see that. So here we've just got some data points going negative, and it'll work out for you exactly what that relationship is all the way through the middle. If points start going a little bit, I think it's this one here, yeah, points start going a little bit crazy, it starts to have a hard time of it. So look, here it's really starting to struggle. So your data points have got to be in, like if you're doing any scientific experiment, your data points need to be half sensible in order for it to work, but I guarantee it will work. Right, I've got another one for you, and this is one of my favorite ones. So I'm going to stop this a second and just change a screen to show you a different one you can play with. And this one is an absolute piece of genius. Again, this is just schoolyard mathematics. Right, you can download this one. So this is called a product moment coefficient, bit of a mouthful. Trust me on the mathematics. Don't worry where they come from too much about standard deviations. Just trust these are correct. Break everything down into tiny bits of mathematics, and then you can see here I've then got a very simple, so the red stuff matches up with the red stuff, I color coded it. The green matches the green and the purple matches the purple. And this will give you a number between -1 and +1. And this is just a small data set, and you'll be able to work out, we'll go back to the screen, this will then tell you whether your numbers are going up, whether they're going down, and how well they correlate to each other. So let me show you that. Brilliant piece of maths. Share screen, different screen, different screen, different screen. Right, this one I like. So we can go back to this one here. So all these points here fairly closely match each other. You'll get a number 1. So it's telling me it's +1, so it tells you numbers are going up. And the higher the number, the better the correlation of the numbers. If it's going down, then you get a minus number close to 1. So that's saying that the data it's got is very reliable. So having now worked out what the gradient is and that the data is now fairly well correlated, you can have a high degree of confidence that what it's learning is probably correct. Now things start to go a little bit pear-shaped later on. So here things are getting a little bit more spread out, you can hopefully see. So it's not quite so sure. So look, saying I'm pretty sure the numbers are going up because it's positive. And I'm pretty sure that they are reasonably well correlated because it's 0.92. And the great thing about this product moment here, which I've done, is because the numbers always, ever, only between -1 and +1, it means you can just use something like an if then else computer statement, in order to work out, am I in a decent range in order to trust this data? And being able to have those numbers between -1 and 1 is what's called fuzzy logic. And a lot of AI is all based on fuzzy logic. There's another one here I've done where the numbers are again a little bit all over the place, and it's now not quite so sure about what it's looking at. So the more conclusions that you can draw from your data. Just like if you're a person doing a job, the more results you have from different angles about data you're trying to analyze and do some learning, the more confident you always are that I've got this right. Whereas if you only have one data point or one set of data, doing anything, whether it's, checking your bank balance or baking a cake, if you've only got one measure of anything, you can't be sure. So the more measures you have for whatever you're trying to do, the better it is. And I've been told if you can get 9 different points of measurement, you're doing brilliantly. I'm managing to do about 5 at the moment. So far we've done 2, which I think work perfectly and I use quite a lot. There is another one, so I'll have to draw do it on the back of here. I don't know if you've heard of anything called random forest. Oh, hang on, I'll have to change camera, won't I? Where are we? Hang on, stop sharing that one. Reshare that one. Right. There we go. Right, I'll start to write random. Right, random forest. If you do a bit of digging, you might actually find this thing here. All it is, believe it or not, is an if, then.
It's 8 o'clock p.m.
Oops, is it? If then else, thank you whoever's computer that was, an if then else computer statement, that is random forest. And it's just a lot of them all nested together. So you'll see it drawn as well. Look, if something, then do that one, else do that one. Right, and now do it again. So that's all, believe it or not, random forest is. It's just a nested if then else statements, and how far you go, I suppose, depends on what your application is. So those, in my view, I've done here actually. We're going to do standard deviations this evening. So something you can do. So if you're taking an Arduino and you're taking, say, temperature, for example, I know, boiling a cup of tea, temperature through the day, you could very easily work out what the gradient is, because we did that equation, if you remember. There we go. You could very easily work out the coefficients, M and C, piece of cake. You could very easily work out using the product moments. There we go. You can very easily work out, is this thing going up or is this thing going down? If you get 0, then it usually means there's no correlation whatsoever in the data. So -1 is brilliant, means good correlation going down. +1, great correlation, things are going up. 0 means it's worse and terrible, which is why you then want to have multiple different measures for whatever you're trying to do a bit of learning on. And we haven't done standard deviations. That might be something we might want to leave, or we could chuck it in. Why not? I've got it here. So standard deviation is another schoolyard statistic. And what it is, it's a measure of how numbers in a data group differ from the mean value. So you get what's usually looks like a spread. If you ever get any books out, you'll see something that looks like, you'll get one of those bell curves for your standard deviation. So another classic piece of statistics, and what you can do, if you actually divide that by the average value, it'll give you a number every time between 0 and 1. So once again in your code, you've only got to have an if then else for looking for values in bands. You might go, so well, if I'm between 0 and 0.1, if I'm greater than 0.1 and less than 0.2, and if I'm 0.2 but less than 0.3, and so on, you can start to try and draw various inferences and conclusions about whatever your system is you're trying to do some AI on. And all of that will fit in an Arduino. So it's not really for using for vision, but certainly for, there's a ton of data you can get off sensors. That's what I wanted to share with you. So thoughts, questions, anything you'd like me to go over?
So why would you want to do this? It's all very well saying, yes, it's going up. How in a microcontrol system, why is that useful?
You might be wanting to say, let's for example, well, it depends on your application, of course, but let's say something which I'm interested in, wind turbines, for example. Now, one of the things in a wind turbine is you want to make sure the thing's properly bolted to the ground, just as an example. Sounds a bit flippant, but you want to make sure the thing's rock steady. So you might be looking, say, at the vibration of something. So if it starts to get worse over time, you want to be able to go and do something about it. So applications like predictive maintenance is where it becomes very useful. So if I had, say, a wind turbine farm, let's say I had 100 wind turbines, that's not unusual. And typically on a wind turbine, you might have 50 different sensors monitoring all things like temperature and vibration. Now, the real life application here, there's one which we're now looking at is, well, so I've got 100 wind turbines and I've got 50 sensors. So I've got 5,000 data streams coming at me. How on earth am I going to prioritize what needs servicing next? So by being able to predict a trend and how good that trend is and get a good feeling of what a system is doing, I can then maybe start to effectively maintain something like a wind turbine. So there's a real life application for sure.
Stephen,
Yep.
can I interject?
Yeah.
So another, I mean, what Stephen just said is absolutely, accurate and fine. And another situation is if you are doing, if your microcontroller is part of a real-time control loop. So your microcontroller is reading some sensor values from somewhere.
Yeah.
And doing something with them, and then activating some control value that affects the system it's sensing.
Yes.
And then the hardware, whether it's a motor or something else, goes off and does its thing, and then that affects the sensor again, and so you have your loop.
Yes. Yes.
Now,
So it's constantly learning.
So if you in your microcontroller pretend that the sensor value that you're reading is absolutely bang up to date, and you calculate your values based on that, and you pretend that that takes 0 time to do, and you write your output to the system, and you pretend that that output takes 0 time to take effect, then you will be stuck, because all of those things are not true. There is real-time delay between all of these things happening. And the way you deal with that is you arrange your system so that you predict what the sensor values that you're reading would be sometime in the future. And then you affect your control signal to be correct for that future time, so that by the time that that control signal actually gets to the right, to the actual hardware, that actually it is that time and it's doing the right thing.
Yes, exactly, exactly.
So I hope that was clear.
Yeah, no, that's perfectly clear, and it gives. I was just trying to bring in some link to something useful, because it's all very nice having your Uno turning an LED on when the thing's going up, but that, you know, we need to. Well, I need to sort of see how that relates to what I'm actually trying to achieve, because turning a LED on when it's going up is not something that you're trying to achieve.
Yeah, absolutely. What I was just going to try and draw here, one of the things which I'm looking at is a lifetime of something. Fortunately, things are never a straight line. In a lifetime of something here, it's a reliability curve, where if you're doing maintenance, well, if you get to this point on your lifetime curve, then your machine has probably completely failed. And if you're in a factory, that would probably cost you a lot of money. So somewhere between complete failure and no problems at all is when you want to say do some maintenance. So this is absolutely okay. And this here, unfortunately, is absolutely broken. So somewhere between the two, you want to be able to do some maintenance. Now, I could do it over here on a schedule, but unfortunately, I'm probably just wasting money because there's nothing wrong. And I don't want to do it too down here, because chances are I might be doing it a little bit too late down here, my maintenance, for example, because any minute the thing's going to stop working. So by using all the maths we've just been looking at, you could probably start to work out where am I on this curve and how quickly am I moving along this reliability, and where would be the best time to want to do some maintenance.
Okay, but it's unlikely you'd want to do that sort of analysis on an Arduino. You'd have that on your PC. You'd be looking at data going back, possibly days or anything else.
Oh no, actually, what I'm looking at is using. I mean, not necessarily an Arduino. I'm just using that as the example, but it's a very simple microcontroller. Let me turn the screen off so I can see you all. I might put my camera back on. If I can work out how the camera goes back on without ruining everything. Right, there we go. Hopefully I'm back there. There we go.
Yeah.
Hello, everybody. Where was I? I've forgotten now. I've lost my thread completely. This happens when you get old.
Yeah, it was how you would use it, or why you would use a microcontroller to.
Oh, that's
do
right.
something
Yeah, I
like
remember
that.
where I was going now. Thank you for the nudge. Right, so one thing which I'm interested in is using a very simple microcontroller to do the number crunching of a sensor at the sensor and create what is effectively metadata. So rather than transmitting a massive data stream, which is going to take up an awful lot of bandwidth, you could just use the things we've been looking at and just transmit the gradient, where the cutoff, the M, the C, and what were the other things we looked at? Product moment, correlation coefficients, and say standard deviation. So metadata, transmit that, and that would reduce the bandwidth, and then you could just prioritize based on the metadata, rather than just having this massive data stream which nobody knows what to do with apart from stick it on a 3.5-inch floppy.
Yeah, so I suppose it all depends, obviously, on what you're trying to do.
Every time,
as usual,
yes.
and generally, as a hobbyist in this sort of thing, you're far more interested in very short terms, such as the stuff that Ruth was just talking about. Yeah, in the same way that you're predicting you know, if you're trying to get an arm on a robot to go to exactly the right place, you need to know how much power to put into that motor to get it to go to the right place, and you need to monitor that it is going to the right place, but you need to know that it's not going to be in the right place before it's ever not in the right place, if you see what I mean.
I understand exactly what you're saying, Derek.
Yep.
Yes.
And there is one other thing, just going back to what Stephen was saying about the metadata. I can absolutely see a very valuable reason for managing for a, so we sort of call it an IoT device, knowing its own metadata. Assuming that it's got some sort of EEPROM so that it can remember things over time, it would be very useful to have, let's say, an aircraft part that knows its own reliability info, so that should that part be moved between planes, it takes that info with it.
Yeah, I think they do usually monitor, don't they, using sensors. So when it gets to its destination, they'll often know what to do. You know, as soon as it lands, you know. So
I mean, if you know a part is removed from one plane and put in another, that the part hasn't lost. You know, that you haven't lost all the info about that part. It's still, you know, the part still knows it, and it still knows that it was getting a little bit wobbly, but it's basically fine, or that it's absolutely a-okay, or whatever it was. You know, storing that info in some master controller somewhere or other is actually the wrong thing to do.
Mm-hmm. Yes. I mean, the other thing also, so I've got one here, as it turns out, would you believe? I've got a box of these things, is, you know, the other reason for small chunks and metadata is, you know, that there's only 32K of flash and 2K of RAM in these tiny things. So really not much space at all, you know, to store a lot of data.
Mm-hmm.
So being able to squash it down is a desirable thing.
Okay.
Anyone else? A bit lively. All gone very quiet.
All is well.
All is well. All is well. What are the other things which I could share? Just thinking out loud. Did have some other notes on AI. So all this is downloadable, so you can actually play with it. There is one fact. I'll go back and I'll show you this. And hopefully the camera will stay alive. But there is a limitation. Let me just which I discovered with this product moment stuff. Let me just share. So there is a gotcha, and I think it's this one here. So as you can see, there is very clear a correlation going on here in this nice straight line. Yep. But the math is deciding that there is no correlation. So this is a limitation of the product moment, is that it only seems to work very well when the data is going, well, that's going down, of course. You know, there you go, -1, or if it's going up 1. Whenever it's essentially pretty horizontal, it then seems to fall apart slightly on you. So, you know, that is, although there's clearly correlation there, it's not actually much better than that, you see, and that clearly's got problems. So you need to have multiple parameters and apply a little bit of like if then else fuzzy logic to work out. So in this one here where things are great, well, look, the gradient is essentially about 0, okay? And if you were to look at the coefficient of the standard deviation, so everything's quite tight, 0.06, whereas here, everything's just a little bit looser. So you could actually, although there's a limitation in the maths, you could actually get around it by doing some conditional testing, which is, I think, what you need to do with a lot of it in the code, which is why it's good to have multiple sources. But just as a word of warning, word of my advice, I could say, I suppose, is whenever I'm doing this, I'm very reluctant to try and do multiple ways of saying the same thing. It's a little bit like if you're not careful, I could do standard deviation, you know, I might look at 2 standard deviations, I might look at some of the others maths you can do. But if you're not careful, it's almost like having a pie chart and a histogram and a scatter graph. It's the same data just shown in a different way, and it's not really telling you anything new. You know, if I had a bar graph or a pie chart, it might look different, but it's actually exactly the same. So there's no new information. So what I'm looking at and what I recommend is that having multiple measures of whatever your system is, but those measures all come at it from completely different angles and completely different mathematics, and you don't end up just convincing yourself of something that's not true, because I think that would then end up with bias in your data. And bias is something we'll talk about. Bias is, you know, convincing yourself something is true when it's not, pretty much. Yeah, that's a worthy point, I think. Did that make the remotest bit of sense to anybody? Let me stop sharing that. There we go.